Thank you, Chakrapani. My name is Tarun. I am here to take the class on behalf of Chaitanya Kumar sir. Today we will discuss about some projects we are going to do in our internship. Let me share my screen. Is everybody can see my screen? Please reply me. Okay, thanks, Moni. Today we will design a digital clock using Verilog RTL code. Here we here we create a set of counters which are suitable for a 12-hour clock, which indicates AM, PM. Here in this Verilog code, we will design the digital clock. Wait, I will show you small diagram. A digital clock, a 12-hour digital clock, which we can see here. We have 2 digits in seconds, 2 digits in minutes, and 2 digits in hours. We'll take 8 bit. We'll take 8 bits for seconds, 8 bits per minute, and 8 bits per hour. Now I will explain the code. At first, while we are writing the RTL Verilog code, the first step is to do module declaration. Here we create a module which is named digital clock. We'll keep it that digital clock. We'll give the inputs clock, reset, enable, and the output pins we take as register type so that we can store the date values. Output pins are for hours we give HH, for minutes and seconds SS. First we'll write the code for seconds. We create an always block triggering on the rise edge of the clock. We'll write if statement if reset is high or the clock is enabled, and the seconds it's a logical AND operation, and the seconds reach its 59th value, the seconds clock will reset again to 00, or else if enable is high, the lower bit of the seconds clock will turn to 0. I'll show you here. When the enable is on, if the lower bit is a ninth, lower bit last four binary digits of seconds clock from the eight bits. If it turns out to be a 9, if it turns out to be 9, we will reset the last 4 digits of the seconds clock to 0. Else, if we have some digits like 8, 8, 7, or 6, 3, 2, any digits, we will increment the digit when the clock signal is given. Did everybody understand about the seconds clock? Please give me a reply. Okay, Bhuvaneshwari, I'll explain that. Simply, at first, we'll consider the always clock and positive triggering of the clock. At the passage of the clock begin. If reset is high, you know the reset signal, right? If reset is high, the clock will begins from 0, 0. If reset is high or logical OR operation and enable is high, enable which enables the digital clock and logical AND operation and the second digit and second digits is 59. This is logical AND operation. If enable is high and the second digit is 59, after the 59 seconds, our minute hand will change and second hand will become 0, 0. We are not writing about the minutes hand here. We'll see that later in the other block. Else if enable is high and the last four bits of the seconds clock is 9, then the passage of the clock enters, it resets to 0, and the first four digits of the block, first four bits of the seconds clock will increase. Or if it is not 9, if we have 8, 7, or 6, anything, the seconds block simply increases its number, last four bits of the second block. And here we said that the seconds block, the first higher four bits of the seconds block increases, right? Here you can see that the last four bits of the seconds block is 9. The first four bits higher bits will increase to 1. Bhuvaneshwari, did you understand the logic? Okay, we'll proceed to the minutes hand. Similarly, we'll consider the minutes hand. We'll create a always passage of the clock. If reset and logical OR operation, enable is high, logical AND operation. If the minutes hand is 59 minutes and the second hand is 59 seconds, then the clock resets. You all know the clock logic, right? How does the clock work? Let's consider current time is okay. Let's consider 1 hour, 59 minutes, 59 seconds. What does the next digit enters? The hours clock will increase to 2, and the seconds clock and the minutes clock resets to 0, 0. We are not writing about here hours digits. We will explain that in another block, another always block. Let's consider only the minutes block here. If reset is high or enable, logical and minutes is 59 and seconds block is 59 seconds, then the minutes block resets to 0, 0. Else, if enable is high and seconds block is 59, in that we'll consider another if block. If minutes hand is 9, then the minutes last lower 4 bits will change to will reset to 0. Else, if they have a number something like 763, it just after the passage of clock, it just increases the value. It will write another clock. The top last 4 digits of the minutes clock is 9, and automatically the top 4 bits, simply you can see here. If here digits, the last 4 bits in the binary code. If you have 9, wait. If you got 9 here, automatically the minutes bit will increase 1. If it is 19, it just changes to 20. It will increase 1 and it resets to 0. That's the simple code here for minutes hand. Now we'll consider the hours hand. Similar to that of minutes and seconds, we will consider an always clock and the passage of the clock when the clock is high. And only that passage of the clock, right? It is the clock diagram. Here the rising edge. The rising edge of the clock is called the passage of clock. And the leading edge is called the neck edge of clock. We can consider anything, but we'll consider here passage of the clock. It's similar to the minutes and second hands. If reset is high, hours clock will enter to 12 because we don't have 00. Here, for hours clock, we cannot write 00. When reset here, we can see in the description. When we reset the clock at 12 a.m., PM is 0, AM is 1, 15, 8, 12, 12. Clock 10%, resets the clock at 12 a.m. Okay, when we reset the clock, it shows 12 a.m., not 00. We cannot have 00 in the hours block. Yeah. If we reset it high, hours block will get 12. In the input block in the model instance, when we declare the model, we have considered the PM output register PM. We consider the type as register so that we can store the value. You can see that PM is 0 for AM. When it is AM, we'll keep the PM value as 0, or when it is PM, we'll keep the PM block as we'll enable the PM block. We'll keep the value 1. So you can see that when the reset blocking shows high, hours block we get at 12 a.m. Hours block will be 12, and the PM block will be 0 at PM. It simply shows that we are currently at AM. And we'll write a else if block. If enable logical and seconds hand is 59 and minutes hand is 59. You can see here. Let's consider it time 0, 2, and we have here 59 minutes. and 59 seconds. When we get a passage of clock, this seconds increases and it resets to 00. The minutes hand will increase and it resets to 00. The hours hand increases from 02 to 03. In this way, we'll write hours logic. It is simple as that. Another replock, we'll write another replock. If hours hand is 11, begin. In this condition, if you have 11 at the hours block, when we increase 1 here, it changes to 12, in which the PM and AM block changes. If it is AM, it will changes to PM. We wrote the code. We apply negation to the PM, and our block turns to 12, and else if hours block is 12, hours block changes to 1, else if the last 4 digits of 4 bits of the clock here, the last 4 bits, total 8 bits, total 8 bits. Here we have 4 bits, lower 4 bits, higher 4 bits. We consider here 4 bits because the maximum number we can get here is 9. Which can be represented in 4 bits. 0, 0. 1 plus 0 plus 0 plus 8. Total 9. So we need 4 bits here to represent a 9 digit. That's why we considered here 8 bits. Hours and minutes and seconds, we consider 8 bit register. If the lower bits gets 9, automatically it resets to 0 and the higher bit increases to 1. Else, if it is something for 4, 3, or 2, it simply increases by plus 1. We will write the code in, we'll simulate the code in EDA playground. I'll open my EDA playground. Here I have written my code in the EDA playground. It is a similar code that I have explained previously. Here we write the test statements for this. Here we take the time scale 1 nanosecond and the precision 1 picosecond. We'll create a module. We'll create a test statements module. Name it as TB underscore digital underscore clock. We just added TB so that it is simple to understand. We'll give the inputs a clock reset register Y, and we will instantiate the digital clock module. Here the module we have given digital clock, right? Digital underscore clock. We'll instantiate the same module here. Everybody knows the instantiation, right? Here we generate the clock. We simply write always #5 clock equals to negate of clock. It creates a clock of 10 period of 10 nanoseconds. We can simply replace the always block with a forever loop. Anything, it's not a big problem. We'll initialize the signals. First, we'll give a clock signal 0 and reset as 1. Enable the 0. Here we write the dump files. These dump files and dump parts. These dump files create a file which is named as digital_.pcd. It dumps the whole values, whole graphs, simulation graphs. If we don't use a dump file or dump parts, we can't get the simulation results. It's compulsory to use them. And dumpers. These dumpers simply dumps the variables, the change of the variables in the file, in the digital file. After 10 clock cycles, we'll reset. We'll keep reset equals to 1, and we'll enable the clock up to 1000 clock cycles. And we apply the reset again to see if the clock resets correctly. Reset equals 0. And we'll run. First of all, save the codes. Select the language which you are using. We are using Verilog language. It's not a big problem. We are not doing any high-level test benches. Tools. We can use any of the tools. Currently, I'll use AllDeck Avira Pro 2023. Time scale, run scale. In runtime, you should always click on Open EPWay after run so that we can view the simulation results clearly. Now we will run the program, run the code. Here we can see the signal. I'll zoom this. Here you can see the clock signals. This is my clock. Enable signal. At first, we'll give the enable 0. Next, after 10 clock cycles or something, enable will be high. We can see that hours at the start of the clock, the hours is at 12 hours, minutes 0 minutes. It's currently at AM. You can see that it is low. We'll give the reset signal 0 here. And seconds currently after the reset signal is 0 and the enable signal is high. The seconds starts to count for every passage of the clock. You can see that here 1, 2, 3. You can see the seconds clock gradually increasing 10, 11, 12, 13, 14, 15. You can clearly see that the clock signal, the seconds clock is increasing. At the 59th second, it just resets to 0 and the minutes hand just increases from 0 to 1. In the similar way, the clock continues for 1000 clock cycles. In this way, we can design the digital clock. Did everybody understand the designing of digital clock? So when will the 00 case in? Boneshwari, can you repeat your question? I can't understand it. Sir, when will the 00 case in seconds? When the seconds clock, when we get 59 seconds, then we get 0, or when the reset signal is high, we get 00. The two conditions we will get. The seconds clock resets to 00. Boneshwari. Okay, sir. Okay. Did everybody understand the designing of digital clock using Verilog RTL? Please give me reply for that. Chakrapani. Okay. Now we will discuss another project which is based on ALU, Arithmetic Logic Unit. I think you know very well about this Arithmetic Logic Unit. For every microprocessor, we have an Arithmetic Logic ALU. It depends on the type of processor, 8 bits or 16 bits, 32 bits. For high-end processors, we have high number of bits. Here we just simply design a simple 8-bit ALU in which it can perform addition, subtraction, multiplication, division, logical, and NOR, XOR, NOR operations, comparison operations. You can simply add or remove some of these operations. It's not a big deal. Here we added all this. You can add some other operations in your ALU if you are designing. Arithmetic logic unit, it is a crucial digital circuit in the computer, the central processing CPU. Okay, let's explain the code. Explain the Verilog code. At first, we'll do module declaration. We'll give it a module name as ALU. We will consider 8-bit inputs. AB as inputs, and we'll select. Here we have so many operations. In order to select each operations, we'll create a register type input and name it as ALU underscore selection as well. Anything. We'll get the output as ALU underscore out. We'll name it as ALU underscore out, which is 8-bit. And we'll add a carryout. We are adding carryout because if adding 8 ones and 8 ones of A and 8 ones of B, we can get a carry. So for multiplications also, we need a carry. If any digits increases, digits from 8 bits to 9 bits, simply the carryout is useful in order to save that bit. Okay. Here we are selecting a 4-bit ALU cell because currently we are doing how many operations? 1, 2, 3, 4. We are doing 11 operations. For 11 operations, we need a 4-bit. We need a 4-bit ALU cell. Okay. We'll define a register result. Will register register. At the end of the code, we will assign this ALU result to the original output ALU out. We'll consider simply register 8-bit register ALU results so that we can assign the result values to ALU result We'll consider a white lab TMP. Something we'll name it as TMP. Assign. Okay, we'll consider the assign statement. Here we have assigned the ALU result output is assigned to ALU out, which we will get in the simulation results at the output of the simulation results. Okay. Assign TMP. Here we're concatenating a 0 bit to A and 0 bit to B. Okay, assign carry out is on TMP. And in carry out we are assigning the 8th bit TMP. Okay, a 9th bit of the TMP output to the carry out. Okay, we'll start the always block, always at the root. Here instead of passage of clock, you have written asterisk symbol. Asterisk symbol means when we keep here asterisk, when we write a asterisk symbol, it's simply whenever the clock signal increases at the passage of the clock or the neck edge of the clock, anytime any change in the values of the inputs, the output changes, it stores the values. The always block activates for any change in the input signals and any change in the clock signal. Always correct. We'll begin the logic. We'll consider a case statement, so it will be easy. If you can consider the if block, but we should write so many of the statements. We should write else if block in every if block, and it would be some hectic. So we'll consider a case block, in case ALU selection. We'll consider the ALU selection in this. Consider the first case. When we have 4 bits 0, 0, 0, 0, and let's consider it as addition mode, addition case. ALU result equals to A plus B. Simply it adds A and B. If any carry operations happen here, the carry bit will enter into the TMP8 and it is assigned to the carry out symbol. You can clearly view that in the simulation results. Okay. We will consider another case 0001. Let us consider it as subtraction. ALU result equals simple 8-bit subtraction A minus B. Similarly, multiplication. We'll multiply A and B. And another 0011 division. We'll just divide A and B. And logical AND operation. Here, these are the operators: logical AND, logical OR, logical XOR, logical. It's simply logical OR. When we keep here negation, it becomes logical NOR. Similarly, logical NAND, logical XOR. Okay. We'll consider the comparison. Here, these are used in the gate level modeling. When this condition A greater than B is high, and it is correct. ALU result. One is assigned to the ALU result, the output, or if it is low, it is wrong. If B is greater than A, then 0 is assigned to the ALU result. It is mainly used in gate level modeling, using gate level modeling. Equal comparison, similarly, same statement. If A is logical equal operation, when A equals to B, not A equals to B, equals to means we are checking a equality condition here. If A equals to B, if it is true, we will assign 1 to the result, else we will assign 0 to the result. Default, if any of this case is not happen, any of the case, if we give 1 1 1 1, it comes under the default statement, and the result will be simply addition of A plus B. And yes, okay, testing. Similarly, we'll write the test bench code for simply. We'll create a module TB underscore ALU. Anything, any name, we can simply write. Register will create the inputs A, B. We'll instantiate them. Here we had instantiate ALU. It's the module name and the starting. It's the main module name. Here we just instantiated and same outputs, same inputs and outputs have been taken here. AB, ALU cell, ALU out, carry out. Hold initial, begin. Clearly, it is a logic. It is a combination circuit, so there is no need of clock. So we don't need to create a clock signal here. We can simply write the code. If it is sequential circuits, we should create a clock signal. So it's no problem. We don't need to create a clock signal here. Hold reset state for 100 nanoseconds. We'll give A value as 0, a hexagonal value, and B as 02, ALU. Selection 0. Hexagonal 0 means it's simply addition. We'll create a for loop so that we don't need to write all the cases, all the selection cases 0, 1, 2, 3. It will be a long process and it will be somewhat hectic. So we'll simply write a for loop here. For loop I equals to 0, I less than or equals to 11, I equals to begin. We'll increase one by one so that we can cover all the cases here, all the cases 0, 0, 0, 0, 0, 0, 1. Cases, okay. We give another, okay, f of 0, 0, n. These are the simulation results. I have done them in Vivado, which is not available to you for now. You can do it in EDA Playground. If there is time, we will do that in EDA Playground. No problem. I'll just show you the results. Here, when the A is 10, we consider the radix as decimal so that we can view decimal digits. 10 and B is 2. Here, okay. When the selection is, okay, sorry, okay, here is. When the selection is 1, we get subtraction. Here we have value 12 because I have zoomed out. I can't see, we can't see the value here. No problem. Here it will, here we'll have the value 12. When the selection is 1, 0, 0, 0, 1, it will be subtraction. Subtraction case happens. 8, 10 minus 2, 8. When it is 2, it is a multiplication case. 10 twos, 20, similar to 3 division. And these are logical AND operations and OR operations. This is the RTL schematic diagram, and which we can do this in Vivado. Okay, it's no need of that, but I just simply took the outputs from it. These are our inputs: A bit, B bit, selection input. Here, here they have used a mux. Simply this, it shows the schematic diagram. It's a gate level diagram of written code. Okay, so we'll try to simulate the code in EDL playground so that we can view the results. Here is the test bench code. We'll just save this code. Okay. We'll consider, we'll click the open EPV after run ALDEC tools. We use ALDEC to Verilog language. We'll run a simulation. Yes, okay. Sorry. I didn't use dump file. Previously, I have said that, but I didn't use them. Wait. You mentioned D. Okay. I'll write dump vars. Okay. We'll save the code. We'll try to run the code. Okay. One has finished. We'll click the get signals. We'll select all the signals. Tap and select. Let's see now. Here we can see when the selection is 0, 10 plus 2, 12. Addition operation happens. Similarly, when the selection is 1, subtraction operation happens. 10 minus 2, 8. Similarly, when the operation is 2, 10 to 20, multiplication operation happens. And it is 3, and division operation happens. 10 by 2, 5. And these are, will for 3, 4, I think these are all logical AND operations, NAND operations. We can understand them when they are in binary format. We can apply AND operations and NAND operations. We'll get the outputs correctly here. In this way, we can simply design a simple ALU. We can design any bit ALU. Here we just simply designed a 8-bit ALU. It's not a big problem to create higher bits. Did everybody understand the design of 8-bit ALU, arithmetic logic unit? Please give me a reply in the chat box. Okay, Shiva Ganesh. Okay. Manikanta, I have just explained, right? Just view the code, you can understand that. Everybody understood the code. So please once view the code, it's not a big deal to understand the code. From here onwards, Sharat Chandra will continue the class. Okay, thank you.
Good afternoon, everyone. Good evening, everyone. Is my voice audible? Yeah, thank you. Today, the Chaitanya sir is on leave for the sick leave. So I and Taran, we both are interns in this Blackbucks. We are taking seeing your projects and all. We are also dealing with the assignments and assessments. I think everyone understood about the LU logic unit and digital clock, which Taran has already said. Uh, Today we are going to learn about the Verilog code on voting machine. Today these electronic voting machines are mostly used in the general elections in our India. Wait a minute, I'll share my screen. Is my slide visible? Radhe Reddy, what is software link? Raj Reddy, can you please respond? What is software link? What do you wanna ask about the software link? Okay. Okay, Raj Reddy, our team will respond to that. We're gonna discuss about the voting machine using Verilog. I'm going to discuss about the gate level Verilog code for voting machine. As you all know, in our country we use electronic voting machines, which contains the control unit. You can see here control unit, which will be handled by a preceding officer, and we use ballot unit, in which the ballot papers and serial numbers or etc. will be available in the ballot unit. And of course, we'll vote on the VVPAT. So we'll write a code for which how the election process will go on, how will cast a vote, how will the ballot unit prints the ballot paper, and how it will store in the control unit. Is that clear? Can you respond for that? Anyone in the chat, can you please respond? Okay, thank you. So our main objective today is to design a simple voting machine using gate level Verilog that counts voting for 3 candidates. So I'm taking example for the 3 candidates. In the voting, there are many people in the booths and all. There are many people voting in the voting machine, but I'm taking example of 3 candidates for the simplicity. To consider this, we'll have to consider the inputs and outputs clock reset for the writing of Verilog code. In this we can see the modules. We can also write the code for ballot control. We are also sorry everyone, there is a technical issue. Let me wait for another 2 minutes. Let everyone join. Everyone, can you see my screen? Can you please respond in the chat? Okay, thank you, Durga. Thank you, Praveen. So, okay, apart from that, can we generally discuss about what should we require for the writing of Verilog code? Can you please respond in the chat? Writing a simple Verilog code for the AND operation or something, or so what we require to write a Verilog code? Can you please respond in the chat? Anyone? Is my voice audible, or is there any technical issue? Can anyone respond in the chat? Okay. So we'll be requiring to write a Verilog code. We'll be requiring a input and a output, or we can connect the clock, or we can connect the set reset. Uh, okay. Thanks, Durga. Yeah, you're closely right. Yeah, Bhuvaneshwar. You're exactly right. Thank you. Yeah. So we are taking this voting machine as a combination circuit, but it's actually a sequential circuit. But we are taking a part of voting machine, but to write a very long code, and not uh, in generally explain how the voting process is going on. But we are writing a part of the voting in the VVPAT. So how it a voter goes and votes the vote, casts the vote, and then how it will um, so how a voter will go and cast the vote, and how the counter counts the voting scripts or in the ballot papers, and how it will store the memory or in the registers. So I'm going to explain the code. If anyone has any doubts in the writing the code, can you please respond in the chat? Okay. So firstly, we are declaring the module like voting machine. In that, I'm taking three candidates as an example of the input. So I'm taking input wire vote one for the voter one, and the vote two and the vote three. So these are the inputs, and to store the register votes in the ballot unit, so we have to count the votes, and we have to store in the register counters. So, we are connecting the counters to the output, so that after the initiation of the port, the signal or the information counted. Okay, I'm connecting to the output paper, output wire. So it is count one, count two, count three. So I'm taking as a 4-bit input. You can see 3:0. So I'm declaring the module as voting machine. Uh, So I'm declaring input wires, and I'm declaring the output wire. So my requirement for the Verilog code is clear here. Is anybody having the doubt in the writing the first part of the code, module declaration? Can anyone respond in the chat? Yeah. Is anybody having the doubt in the module declaration part? Okay, thank you, Parvati. And Mauni Shande, the team will get back to you. Oh, you didn't understand. So basically, we are declaring the module. So we are taking the input as three candidates, vote 1, vote 2, vote 3, and it has to be counted how many votes a person got. So we are connecting to the counter. So it will count 1, count 2, count 3. So that count 1 will count the votes that are preceding the vote 1. Count 2 will count the preceding of vote 2. Count 3 will count the preceding of vote 3. So we'll get the list of how many votes that are been casted by all the people. So then we will connect to the register. So it has to be stored until the election results has to become. So we'll connect it to the registers. So is that clear for the modulation part? Parvati and Shiva Krishna. We are just writing the input and output part. That's it. We are not being gone through the whole topic. Okay, thank you. Thank you. So we are taking this part as a combination logic, so that we are taking this always at the rate we are taking not taking the posits of the clock. So we'll get some errors for this, but if we take the sequential circuit for this whole the voting process, will not get any glitches or any hazard for this process. So for this modulation part, we have already given the input and output parts. So the input wire vote 1, vote 2, vote 3, these lines declare three input signals. Each input wire represent a vote, and output count 1, count 2, count 3, these lines declare the 4-bit output signals. Okay, then we go into the internal registers. Okay, so we are taking the register count 1 register equal to 0. These lines declare the 4-bit registers. So to store the data for the votes, we have to initiate the internal registers. Okay. So anybody having the doubt, those two people raise hands. Galaxy, someone? You're having any doubt? Please put your doubt in the chat. So until we'll continue. So we are declaring the internal register to store the vote counts. Okay. So we're declaring the 4-bit register, initializing to 0. So first of all, we'll try to insert like 0. So we are starting from 0 vote to how many vote we are getting for the each candidate, vote 1, vote 2, vote 3. So after that, we'll count all the votes. So then we will declare who won the elections. So this is the process of writing the code. So firstly, we'll start from counting for each candidate, vote 1, vote 2, vote 3. Okay, then we'll go into the combinational logic units. So we'll begin here. Always at the rates. This begins an always block that will be executed whenever any input it is sensitivity or changes. When the positive edge or negative edge come into the procedure, it will store the value of what we are declaring, what we are casting the vote for the vote 1, vote 2, vote 3. Okay, then we'll see here if conditions, if vote 1. So if any of the candidate for a voter 1 or voter 2 or voter 3, if they got any vote, so the counter will counts the uh, ballot papers in the ballot unit. So they'll have the voting count all through over the election. Okay, so it will count for the voter 1 candidate. So I'm taking here vote 1, so it is like candidate 1. So vote 1 will get the vote if anybody cast the vote for the candidate 1. Okay, we'll go to the if conditions are for that. So to count the every information or the data is raised to positive edge, so the counter will count the value. So there is an increment for each and every vote. Okay, we'll go to the assign. So output assignments. So assign the value of the internal register, count register to the output file. So we'll assigning for every counter to the register so that the counted values of the candidates can be stored in the registers. Can anyone say the difference between the register and the memory in the chat? Can you please respond? We're storing the data in the registers, the counted values in the registers. So what is the difference between a register and a memory? Can you please respond in the chat? Is my voice audible? Can you please elaborate, Manikanta? What is the difference between a register and a memory? Both will store the data. How it will store the data in register and a memory? Okay. Yeah, you're right, Hemant and Shivakrishna. You're close enough. Like, yeah. Anyone with another answer other than Shivakrishna and Hemant? You're right, Nagendra Babu and Praveen also. Yeah, you're right. So a register holds the operand or instruction that CPU is currently processing. So what CPU is currently processing uh, that will store by the register, and the memory holds the instruction and the data that the currently executing program in the CPU requires. So what the CPU requires currently that will store by the memory. So this is a basic difference of the register and the CPU. So we'll use registers here so that the instruction that CPU is currently processing. So the words are processing in this code so that we are using the register. Okay, so basically we initiated the inputs and we initiated the outputs. So what we call module description, and we initiated the internal register to store the counted values of the votes. Okay, and we assign the counters to the register. So after the counting the votes, we will store it in the register for the counting process. This is the source code of the Verilog, the gate level code. Okay, everybody understood? Is anybody having the doubt in the source code for the voting machine? Can anyone respond for this? Okay, thank you, Praveen. So we'll go to the test bench. So firstly, we'll discuss about the module declaration and parameters. So for this, the test bench, the module is named after voting machine TV. You can find here. Yeah, voting machine TV. So for this, we assign the parameters at 10 nanoseconds for the clock period, so that After every 10 nanoseconds, the other vote will be counted. Okay. If we not mention any parameters, the vote will be like biased. So after if one candidate go and votes the vote, it will be repeated for the playback, so that only one candidate will get the whole votes like this. So for that, we are mentioning the parameter for the 10 nanoseconds. Okay. And we're going to the signals. So we are initializing a signal. A clock is we're taking clock signal, vote inputs, and vote count outputs. So for the clock signal generated with a period of 10 seconds, you can see here. And the vote inputs, vote 1, vote 2, vote 3, are register used to simulate the vote inputs. So these are the these are to insert the registers. Okay. Then we are also mentioning the signal for the vote count outputs. Like count 1, count 2, count 3 are the bytes used to capture the vote counts from the voting machine. Okay. These are used for to count the inputs from the vote 1, vote 2, vote 3 for the uh, contemporary count 1, count 2, count 3. Okay. Then we instantiate for the voting machine model. So how it will work. Okay, the source code is used to give the how the process will work, and how the process will be working is given by the test bench. Okay, then we'll go to the voting machine instantiation. So the vote machine, the module you can see here, the voting machine module. Okay. So we will devise. So the voting machine module device under test. So you can see a DUT here. So this is device under test is instantiated with connection to these vote 1, vote 2, vote 3, and count 1, count 2, count 3. So how the votes are instantiated and how the counting counters are gonna count the all the votes happen in the elections. Okay. This is a general clock generation of the clock. So here I am taking a period by 2 clock for the negation of the clock, so that for every time period it's gonna count the uh, voting process. Here I can take the test samples. So firstly I'm initializing, then beginning with the dump file, so that these whole data of the test bench will be stored in the dump file. Okay. Then we are initializing the votes. Firstly, we are taking vote 1, vote 2, vote 3 are 0. So nobody is voting in the ballot vote. So then the counter will take the values of 0. So there is no voting occurred when there is vote 1 is 0, vote 2 is 0, and vote 3 is 0. So it will wait for the few cycles, 10 seconds, because we are initiating with the period 10 nanoseconds. So it will wait for 10 nanoseconds. Then it will again take the inputs from the preceding officer with the control unit. For that, vote for candidate 1, comma 2. So how many? So vote 1 is occurring 2 times. So it's like vote 1 equal to 1. So it will wait for 20 nanoseconds. Then vote 1 equal to 0, and it will wait for 20 nanoseconds. And vote 1 equal to 1, it will wait for 20 nanoseconds. And then the last vote 1 equal to 0. So these are the inputs, how the inputs are going to the vote 1. Then we are going to the vote 2 for the candidate 2 3 times. So we can give any number of inputs for the vote 1, vote 2, vote 3. So these are the inputs 1 0, 1 0, 1 0 for the vote 2. So between them we are having a 20 nanoseconds for each. Then we are only taking one time for the candidate 3. Vote 1, vote 3 equal to 1, and vote 3 equal to 0. So these are the test cases in the test bench. How the vote 1 is going on, vote 2 is going on, vote 3 is going on. Then it will go for the counters to count the votes, number of votes. Okay, here we are ending this simulation. So it is this finish symbol is used to terminate simulation after all test cases are executed. So we are ending it. So we're also using display results. So and always pause at clock begin. Block is used to display the current vote counts. Count 1, count 2, count 3. Whenever there is a positive edge of the clock, uh, the counting it go on. Then we are ending the module. This is the test bench for the voting machine. Is everybody understood this concept of for the Verilog code voting machine? Please reply in the chat. Thank you, Hemant. So we'll see now the EDA playground how it is working. Okay, so everybody can see my screen, the EDA playground in the background.
They're not internships, yeah, students for learning from Blackbucks. Unquote. But
So we're putting here the source code and the test bench. Save here. So I think Tarun has said how to run a EDA playground. So I'm taking the test bench plus design as system. I'm initiating the Verilog code here. And tools and simulators, I'm taking the Aldec Riveria Pro 2023.04 because these are all commercial simulators. So we have to, I think these three majorly, we have the license for these, all this. We don't need the license for Aldec Riveria. And there are free simulators. You can also use this, but I'm using the Aldec Riveria. So I'm selecting the OpenEP waveform so that I can get the waveform at the end. So I'm saving it. Yeah. Yeah, okay. This is the waveform that is generated with my code. So you can see here clearly when a candidate one for the vote one goes and vote to a vote one person. So it is showing in the counter is like 1. So this all through case for the 10 nanoseconds, it is showing like 1 because it should not be over terminated. For the different person comes and votes to the same person also, it should not be merged with the vote. So it has to be counted in this ballot unit. So for that vote 1, you can see here clearly you can see a counter is initiated in the count 1. So for the count 2 here, so when another person go and votes to a person 2, so it is counted in the counter 2. So if anybody goes and any person uh, goes and votes to a third person, it is counted. Okay, you can see you can also try in the EDA playground. So this is very interesting project. This is a EVM machine. So I'm taking only the some part of the voting process. I did not have taken all the process in the unit. So it is like there are 3 parts. So I'm explaining the general procedure of how the code runs in the
it's because they trust me or
elections. So firstly, we'll have a 3 parts: control unit, and ballot unit, and VVPAT. So control unity is managed by preceding officer. You can see here. So you can also write the code for this by using LED light program. So how it will, so you should initiate a input from the preceding officers. It is like positive words from the preceding officer, so that the ballot unit is initiated to cast the vote. So it is ready to take or count the vote from the control unit. So you should write the code for control unit. Then you should also write the code for ballot unit. So if you are really interested in writing these Verilog codes, so it's very interesting project. So you should have to write the code for whole control unit, ballot unit, and VVPAT. So in the ballot unit, you have to write the code initiating. I have already discussed like inputs, output, clock, and reset. So reset is used when the process is starting, election process is starting. So I think you have very much known about the mock process held before the election process. So all the receiving officer and the other officers also cast the vote in that to that so that they tally all the votes in the ballot paper and the EVM so that they'll tally is there any misguiding is there from the ballot unit. So I've already discussed the Verilog code for the ballot unit and VVPAT. So acknowledging it, we should have also put the LEDs for the all the control unit, ballot unit, and VVPAT. So when there is a positive edge from the control unit, there is a light blown LED light blown in the control unit and then ballot unit and the VVPAT, so that the person who is casting the vote in the elections is ready to cast the vote. So there is a simple code I could explain you in the EDA playground. So this is a simple code for LEDs, LED control. So this is the simple. So firstly, we are initializing them. We are declaring the module declaration. So it is like LED control. So we are giving a input wire. It is like switch and output wire LED. So we are assigning LED equal to switch so that when we give a positive edge to the switch, the LED is blown. So we are running the module. This is the source code of the LED, and then we are going to the test pins, how the switch will operates, how the test cases in the switch operates. It's like so we are initializing and so we're declaring the module. So it declares the test bench module named LED control TB. This module is used to test the LED control module. So then we are going for the signal declarations. We have a register switch. A register type of signal named switch is declared to drive the switch input of the LED control module. In the test benches, the register type is used to drive the signals. And we have a wire LED. A wire type signal named LED is declared to capture the LED output of the LED control module. It is also used for connecting output to inputs. Then we are going for the module declaration. Okay, this is instantiating the LED control, how it will go on work all the time. Then we are going to for the test sequence. So when the switch ons, so will on it for 10 nanoseconds. Then it will gonna off for the switch equal to 0. Again, it will on when the switch equal to 1, and it will wait for 10 nanoseconds. We are mentioning the period for the clock because when we are giving a input sequence or input information with the switch, there is a no overlap between two instructions. Okay, this is not the pipelining case where you are executing two or more instructions to get the overall performance of the CPU. We didn't want any performance in the CPU, but we are just executing instructions one by one after 10 nanoseconds, so that we'll get the output like. So I'm initialized here dump files also for that it will be saved. I'm saving it. Then I'm gonna run it. Yeah, you can see when my switch is on, the LED is on for the 10 nanoseconds, for 10 nanoseconds to 20 nanoseconds. Okay, so when I'm gonna off the switch, so the LED is off. So you can also try it in the EDA playground. Okay, Is everybody understood the LED control for the Verilog gate level code? Can anybody respond in the chat? If you have any doubts in the voting machine or in the LED, you can please ask me the doubts. Is anybody having the doubt in any of my projects, LED or voting machine? And I'll show the block diagram of the voting machine, how it will works. So this is the block diagram for the voting machine. Okay, Nagendra Babu, what is which code you are asking the test pins for the LED or voting machine? Okay. So firstly, we are declaring the module LED control TV for the test bench. Okay. So the module LED control test bench declare the test bench module. Okay, the module is used to test the LED control module. So as we declared the LED control module here, so we should also take LED control TV for this. So we are declaring the module. Then we are going for the signal declarations. So how the switch will work, how for what inputs the LED is blowing. So we're taking a register switch. Okay, a reg type signal name switch is declared to drive the switch input of the LED control module. So when we are giving any input to the switch, so the LED should blow. Okay, for what inputs it is blowing, we are declaring in the test sequence. Okay, then we are also declaring the signal declarations like wire LED. You can see here a wire type signal named LED is declared to capture the LED output of the LED control module. So for what inputs of switch, the LED is blowing, so it is it is declaring the signal declaration like wire LED. Then we are instantiating the LED control module. So it is like LED control unit. You can see this line. You can see this line LED control unit. So it is a module within the test bench. This instance is named like unit under test. So you can see DUT in the other case, that is dpage under test. This is UUT, unit under test. So it is like so we are giving input to the switch. So how it is impacting the LED. So we are declaring here. So the switch and the LED ports of the LED control module are connected to the corresponding signals in the test bench. So it is like when we are going to the test sequence. So we'll wait for 10 nanoseconds. Will not give any type of information or any input for the device. So that after 10 nanoseconds, we'll start like switch equal to 1. So for this, LED is gonna on for the high positive edge. So for the switch equal to 0, the LED is gonna off. For the switch equal to 1, again after 10 nanoseconds, the LED is closed, and the switch equal to 0, the same LED off. So we are ending the simulation here. So we are going to use the stop function here. So then we'll initial and begin the code once again, so that we are going to insert the output blocks. So to monitor and display the values of signals during the simulation, we'll use this initial and begin. After we also used here initial and begin in the test bench. So this we will use to monitor and display the output for the source code. Okay. Okay. Here we are using dump file and dump bars so that we will save here. So I'm using the same inputs as I have used in the voting machine process. I'm using the system Verilog and Aldec Pravaria Pro 2023. So I'm running the code. Getting the results. Yeah. Anybody having the doubts? Is the doubt clear? Nagendra Babu, can you please respond? So where you're having the doubt, I'm going to show you once again. Yeah. Can you please type in the chat so where you are having the doubt? అంటే నాది లాగౌట్ Can you please type in the chat where in which part of the test bench you are having the doubt? Okay, I'll explain the test bench also for the voting machine. On Nagendra Babu, you're not typing anything, so okay. Where does we connect this switch to the LED? So it's like connecting a simple connection on the breadboard. You can see we'll connect the source to the LED positive edge and the ground to the negative edge. So we are just giving the VDD to the LED. Okay. So in the module, we are instantiating LED control under test unit under test. So in this, for what values for the speech, the LED is taking input and giving the output. So in the initializing part, we'll see. So basically, in the source code, we will assign LED equal to switch. So for what value of the switch, the LED is giving the output. So we will give the uh, connection for the switch for the LED switch and the LED. So in the test bench is used only how the input process is working, how we are giving how many bits of the input we are using, and how the switch is working. We are only processing that in the test bench. We will give the input, output, and the connection for all the inputs and outputs in the source code itself. So here we are taking the input as switch and output as LED. So we are assigning so that we are giving the connection for the LED. So for what values of switch, my LED is gonna blow. So we are giving connection here. It's a simple kind of connection for the LED. Is there any doubts other than this test bench? No. Is anybody having the doubts? Can anyone please respond? Is anybody having any doubts? Okay, thank you, Suresh. Thank you, everyone. I'm going to end the meeting now. You can fill the attendance form. You can leave. Thank you. Thank you so much.